Hello. In this video, we are going to do trigonometric integration. What I would like you to do first is do these one, two, three, four problems. There's some U sub, and then there's one where I want you to FOIL here. You can either do them on paper, or at the boards, whatever you want. So please pause this, do all four problems. The last one, I want you to FOIL it out. Should specify that. So go ahead, hit pause, do all these. Oh, and then one thing, this one, I tried to rewrite it for you so that you could see what the U sub was, the sign to the fourth. I didn't do that for this one. So go ahead, get them done. Here come your answers. All right, hopefully we're in agreement here. The first one, these are all U subs. The first one gives me a negative. That's because the cosine derives to a negative sign. A negative cosine of x cubed plus a constant. Next one is 1/5. I do power rule on this guy, on that to the fourth power. So I get sine to the fifth of x times a 1/5 plus a c. And then the last one, I get a negative because we had a cosine that we were integrating. So a negative 1/9 cosine to the 9th of x plus a constant. Hopefully you're good with those. We're going to do a ton of that in this lesson. And then this will come up, foiling things out. You might have to do some bigger ones, and I'll give you some tricks with that using Pascal's triangle. But we got x minus 7 squared. That gives me x squared minus 14x plus 49. All right, so let's pop into what we're going to do. So next, I am going to draw a little right triangle, and I'd like you to draw this with me. I'm going to label that as theta. I'm going to label that as a right angle. I'd like you to label the opposite, the adjacent, and the hypotenuse for this thing. I'm just going to call this O. I'm just going to call this A. And I'm just going to call this H. Hopefully, we have the same thing. Next, what I want you to do is apply Pythagorean theorem to this. And I'll go ahead and do it with you. I'm going to put O squared first. We would usually, it's the legs squared added is the hypotenuse squared. Usually it's A squared plus B squared is C squared. We're doubly using some letters here, and there's a reason I'm doing the O first. But O squared plus A squared equals H squared. Applying Pythagorean theorem. Now what I want you to do is divide everything by H squared. And then what I want you to see is that on the right side we get 1. And then on the left side, I have O over H squared plus A over H squared is equal to 1. And that, oh, snap. What's O over H in a right triangle like that? It's sine squared of the theta plus what's the A over the H? Cosine squared of the theta equals 1. This, you should know this already. It's called the Pythagorean Identity. We're going to use it a ton in this lesson. I wanted you to make sure that you could see where it came from. Additionally, there are 5 other Pythagorean identities. Five other Pythagorean identities. And if you know where the Pythagorean theorem, or if you understand what process that we just did, then you can get to any of the other ones pretty easily. Let me take this original O squared plus A squared equals H squared. So to get to this identity right here, we divide everything by H squared. If, say, for example, I wanted an identity that involved tangent, or tangent squared, well, what could I do? I could divide by A squared, divide by A squared, divide by A squared. Why did I divide by A squared? Because tangent is opposite over adjacent. So by dividing by A squared, I know I'm going to get an O squared over an A squared. If I simplify this, this gives me tan squared theta plus 1 is equal to secant squared theta. So if I needed an identity that involved one of these two, I could do that. I guess I'll go ahead and point out right now, this can be manipulated in two ways. I could solve for sine squared, or I could solve for cosine squared. If I solve for sine squared, it would be sine squared equals, right? And what would I do? I'd subtract the cosine squared. So I get 1 minus cosine squared theta. Similarly, I could do it the other way around. Cosine squared theta equals 1 minus sine squared theta. So those are two forms of this upper identity here. So what are we doing? When we get into double integrals, there are all kinds of integrals that show up that involve sines and cosines, and we need good ways to solve them. So the tricks that I'm teaching you right now are all things that are going to come up repeatedly as we get into double integrals, and this will eventually be an instinctive process. So today we're doing tricks for solving integrals that involve sines and cosines that are not yet in your toolbox. So let's just start with an example. First example, say I had the integral of cosine cubed x times sine to the fourth x dx. So let's talk about how this one is different from the ones before. Up here, these two, numbers 2 and 3, I had the du for the sine. Cosine was the du of the sine. I had the du of the cosine for number 3. Sine was the du for the cosine. So the key here is that I had my cosine to the first power, so I could do an easy u sub. Same thing here, sine to the first power. Come down to the one that I just gave you. Cosine cubed x times sine to the fourth x dx. Notice neither one of them are to the first power. The cosine is cubed and the sine is to the fourth. So I can't easily rip a u sub out like we did with the previous one. But what I want you to see is that I can quickly rewrite this. Cosine cubed is the same as cosine x times cosine squared x. And then I'm just going to copy my sine to the fourth x dx. So notice I now have, all I did was split that cosine cubed up into two little pieces. And one of those pieces would be a u sub for a sine function, right? So what I want you to see now is that I can replace this right here, my cosine squared x. Well, I know cosine squared of theta, which cosine squared, I can replace that theta with an x, is this right here, 1 minus sine squared of that thing. So what I'm going to do is replace my cosine squared with a 1 minus sine squared. So let me get my pen. This is the same as, hold on, the integral of cosine x, that's the original cosine, times the cosine squared x is going to get replaced with a 1 minus sine squared x, and then times sine to the fourth x dx. All right, so at this point, I can start using u subs. Notice I've got sine squared x and sine to the fourth x, and I've got a cosine of x. So what I'm going to do is let u equal my sine of x, and then my du is equal to cosine x, and I'll write the dx, although oftentimes we just leave it off, but it's there. And here's what's going to get replaced. This sine is going to be a u, and this sine is going to be a u. And then this cosine is going to get replaced with the du. So what are we going to get? This is the integral, And remember, a lot of times, like with this one up here, hopefully, we'll like reorder the du's and the u's, right? So come back down here. That cosine is just going to become the du. So I'm going to write 1 minus the sine squared is a u squared times sine to the fourth is u to the fourth. And then algebraically, I just move the cosine over to the right side, and it becomes part of the du. So at this point, it's almost an easy power rule. It's just one where I have to simplify it first. So this is the integral. If I use distributive property, I get u to the fourth minus u to the sixth. When I do the exponents there, it's u squared, 2 u's multiplied by u to the fourth, so 4 u's, so total 6 u's. I don't know. Oh, yeah, that's correct. Du. And then from here, just quick power rule. So what do I get? 1/5 u to the fifth. That's my power rule on the first term. Minus 1/7 u to the seventh plus a constant. And then my last step is just to sub back in my u. Remember, u was equal to sine. So I get 1/5 sine to the fifth of x plus, sorry, not plus, minus 1/7 sine to the seventh of x plus a constant. So, bam, we're done. We got, oh, I got my plus c. We got the integral of this thing. What I want you to notice is that previously we would have thought of this as an impossible integral to do based on at least the tools that we had. So what I want you to see is that it's an easy sub. We are, in general, looking for the one that has an odd power in order to do this integration. We have other tricks for ones that have only even powers. So, for example, if I had cosine squared x times sine to the fourth x dx, you can imagine I wouldn't be able to manipulate this in a way where I would be left with just that cosine x. So we have to use a different technique, and we'll get there. But if I've got something that is odd, has an odd power, then I can go ahead and do this substitution where I take just one little piece out. I'm left with an even piece like this, and then we can use whichever formula is most appropriate. So I'm going to stop this video here. I'm going to give you one more that has a little bit more complicated problem, and then you're going to do some problems on your own. Peace.